Today we're going to start a brand new unit. Unit 13 is called Transformational Geometry. I think you'll find this unit a lot easier than the trig unit. Today we're going to examine different types of symmetry. You can use the date of May 18th. This is the note packet that you should be looking for. This should have arrived last week in your round 3 materials. I'm also going to attach a digital copy just in case it's out of order or you can't find it. The first type of symmetry is called line symmetry, and this is something that will occur when two halves of a figure are mirror images of each other, each lying on opposite sides of the line. So maybe the left and the right are identical, or the top and the bottom are identical, but there should be all points identical contained in both sides of the figure. The line of symmetry may not necessarily be drawn on the figure, but it is a line that you can place so that it divides the figure into two equal parts. When we work with line symmetry, you should know that it is two-dimensional, so we'll be working with flat figures. In the first picture, we're just going to focus on the bridge structure, not the cables or the flag or the light in the foreground, just the bridge itself. If you drew a line of symmetry vertically from the top straight down the bridge, we know that the left side of the bridge and the right side of the bridge would be mirror images of each other. In the second picture, we're taking this from nature. The trees happen to be reflected in the water, but if you draw a horizontal line of symmetry along the shoreline, just like my arrow is, that would be where it divides the picture into the two equal halves. In our third picture, we have the Starbucks logo. Ignore the little TM trademark. We're just going to look at the logo. If you drew a line of symmetry vertically, starting at the top of the logo, right through the star, and then through the image, the left side and the right side would be identical. So we would have a vertical line of symmetry. In each of our last 3 pictures, we only had one line of symmetry, but it is possible for your figure to have multiple lines of symmetry, and it just depends on what the object looks like. So in the first top left image, we have a square. In this image, we actually have 4 lines of symmetry. Not only is it horizontal and vertical, but it's also diagonal. Remember, if I were to fold along these lines of symmetry, my left side and right side, or top and bottom, should match exactly. In the X, we only have one line of symmetry, and we can see that the bottom portion of the X is thicker than the top portion. In this puddle, we have horizontal and vertical line symmetry, but again, every point will line up. And in this last object, there are no lines of symmetry, and that is possible. In a circle, the diameter is directly in the center of the circle. We can draw an infinite number of diameters into the circle, and therefore it would actually have an infinite number of lines of symmetry. So all figures are just a little bit different. The next type of symmetry is called point symmetry, and basically you have a figure that is built around a center. This King of Hearts playing card does have a center, and it would be located right here in that black box in the center of the king's belt. If your object contains point symmetry, we should be able to spin it and have it look identical. And you can see it does go back to 360, but when I spin it at 180 degrees, the King of Hearts looks exactly the same. The center, though, has to be located on your figure, and we did that. What you want to realize with point symmetry is that for every point on the figure, there is another point directly across from it, but you must pass through the center of rotation In math, we call that the midpoint, and we have talked about midpoint before. So this black box on the king's belt is our midpoint. And if you were to take the K, it would travel to the midpoint, and then it would locate across from it. If you look at this image of two line segments, P is the midpoint for the line segment. A would travel to the midpoint, whatever distance that is, and it would then travel the same distance to locate A prime. The same thing is true with C and C prime. You have to travel through the midpoint, but you're traveling equal distances. So again, if your figure has point symmetry, when you rotate the figure 180 degrees, it should appear unchanged. We have a swirl contained in quadrant 1. If we rotate this 180 degrees, the swirl will end up in quadrant 3, or vice versa. But the center of rotation is right here at the origin in the center of my grid. So if I rotate it, you can see at 180 and then again at 360, it's an identical image. Our third type of symmetry is called rotational symmetry, and we did see that a little bit with the last set of images. With rotational symmetry, you do want to identify the center of rotation, but it doesn't have to be specifically 180 or 360. It can be some angle measure between 0 and 360. My star has a point at the top. It is possible for me to turn this star either to the left or to the right so that another point does take that top position. When you rotate the star about its center, what you're going to find is there's going to be a certain number of positions that will all make it look identical to its original home position. We call this the order of the symmetry. This is a six-sided figure. It's a hexagon. They're showing that you're turning it 60 degrees. So this corner in the top right would actually end up as the corner in the top left. But then this corner in the top left would move down to the side. So as you turn it, the points on the figure are turning as well. For the star, this top point might turn and become this location on the left. And then this location will move down to the bottom left, and so on. When you want to determine the order of the figure, the last rotation returning you to the home position indicates the order. If an object does not have true rotational symmetry, it will take a full 360-degree turn to get it back to its home position. Think about a human being. Head should be on the top of the shoulders. It would take you a full 360 degrees to rotate your human to get the head to be back at the top of the human. So humans have an order 1 rotation. In this figure, it looks a little bit strange, but it does have symmetry. Each of these curved points represents a vertex on your figure. When you count them, you're going to see that there are 8 of those points. That tells me it would take 8 turns to get this position all the way back to its home location. So the order is 8, and we're just counting the vertices on the figure. How many degrees, though, to make this top point go to this next location? Because we're using a circular motion, we're going to take 360 degrees. We divide it by the number of corners on the object. So every time I turn this object 45 degrees, I will get an identical image. We talked about the star. So if you count the vertices on the star, we're going to see that we have 5 vertices. So it would take 5 rotations to get the original home position back to its location. So this is in order 5. How many degrees am I turning it, though, to get an identical image? Again, we're going to take 360. We're dividing by the number of vertices. So every time I turn my star 72 degrees, I'm getting an identical image. In this last figure, we have our hexagon. We have 6 vertices. So this has an order of 6. It would take me 6 turns to get my original positions back to their home location. And how many degrees am I turning it? Well, you can see it in the figure, but you would take 360 divided by 6, and you would see that every time I rotate this object 60 degrees, I will get an identical figure. Your homework is 2 pages long, front and back. It says types of symmetry on it. If you have any questions going through this assignment, please let me know. And we'll have to look at our calendar to see which homework number this is because I did not check. Please get in touch with me if you have any questions. Have a great day.